Hey, suppose we are looking at in a three-dimensional space, and these are the three axes: x-axis, y-axis, and z-axis, like this: x-axis, y-axis, and z-axis. And we are interested in any point in space, any general point. Suppose we are looking at a point here, x, y, and z, and the point is here. So the position vector of this point will be the line joining the origin and terminating at that point, starting from origin and terminating at that point. Suppose the position vector of the point is this. Now what we are interested in any general vector, the vector could be like this, 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 it could be any general vector. We are interested in resolving that vector along each of the axes. As we did for two-dimensional, so we will do for three-dimensional. Now, if in two-dimension what we did was, I'll just remind you one very important thing that we will be doing rigorously as we move ahead. If we had a vector which made an angle theta with x-axis, when we were looking at the resolution of a vector in two-dimension, and this vector, let me call it as R. This R vector had the component along x-axis. We learned it as R. X component of R vector is R cos theta, because theta is the angle which the vector is making with the x-axis, and the component along y-axis, I cap, Ry vector was R sin theta, j cap. Now this was because the angle which this vector makes with the y-axis is 90 minus theta. So R cos 90 minus theta is actually sin theta. So what I'm trying to highlight here is, if the vector makes an angle theta with a line, then the component of that vector along that line is magnitude times cos theta, theta being the angle between the vector and the line. Right? So this is how we resolve, and this is basically the idea how we do. So the same idea, same concept will extend in three-dimensional geometry as well. If we have three axes like this, and we have a point here like this, and if we have the luxury of knowing the angle of this vector, angle between this vector and x-axis, angle between this vector and y-axis, this angle, and angle between this vector and z-axis, this angle. If we know all these three angles, then the approach is straightforward. The component of this vector along x-axis will be magnitude of vector times cos alpha, if alpha is the angle between vector and x-axis. Similarly, the component of this vector along y-axis will be, suppose the magnitude here is r, it will be r cos beta, if beta is the angle between the line between y-axis and the vector. Similarly, the component of this vector along z-axis will be r cos gamma, if gamma is the angle between this vector and z-axis. It's pretty straightforward. So if we have a vector, r vector, and we have the luxury of knowing the angle between the vector and the axes, then that vector can be simply written as r cos alpha I cap plus r cos beta j cap plus r cos gamma k cap. Simply. So there is nothing new here. Cos alpha is equal to Rx upon R. Because Rx, the x component, this whole thing R cos alpha is the x component. I'm representing it as Rx. Rx is R cos alpha. The component along x-axis is R cos alpha. So cos alpha is Rx upon R. And we represent it as L. Similarly, cos beta would be Ry upon R, M. And cos gamma will be Rz upon R, N. Now this L, M, N are called direction cosines. They are important. Direction, because if we know the angle of a vector with axes, we know the direction in which that vector is pointing. And since the function is cosine function, having those angles, so it is called direction cosines. L, M, and N. L specifically is used for cos alpha. Alpha specifically is used for the angle between the vector and x-axis. Similarly, beta for angle between the vector and y-axis, and gamma with the z-axis. L, M, and N. Now, it won't take you much of time and energy to realize one of the important relation here. L squared plus M squared plus N squared is equal to 1. This is pretty straightforward, and you can see this through right away. So if this is not very natural and you cannot see this just at once, then actually put your mind together and figure it out why L squared plus M squared plus N squared should be equal to 1. You should be able to. It's pretty easy. Okay. Now given the components, given that you know the angle, and given that you have resolved the vector along x-axis, y-axis, and z-axis, now suppose you have written the vector in this form. R vector you have written as Rx I cap plus Ry j cap plus Rz k cap. Now, you should be able to figure it out that the magnitude of R vector would be simply, as we used to do for 2 dimension, Rx squared plus Ry squared plus Rz squared. Because when you have a vector like this and you have resolved it along x-axis, y-axis, and z-axis, then if you just look in 2 dimension, then we have seen before that the component along x-axis and the component along y-axis, the sum of the square of that gives the square of the net component. If this is the axis and we have this as y component and this is x component and there is some z component, if we are just looking at these two, then root over Rx square plus Ry square is actually this length. From the vector addition we have seen before and practiced many problems, and so this actually represent this length. If we club it with the component along z-axis, then this component along z-axis is actually perpendicular to this line. They again form a right angle triangle. If we apply Pythagoras theorem once again, that means Rz squared plus root over Rx squared plus Ry square whole square, then this should give you the square of the magnitude of the vector that you have resolved. This should be equal to R square, using simple Pythagoras. So from here we get that R is equal to root over Rx square plus Ry square plus Rz square. Basically, it's just the extension of the formula that we have studied in 2 dimension. Okay, so this is how you easily resolve a vector along x, y, and z axis. So it's a simple, it's as easy as candy. Just as you did for 2 dimension, you do it for 3 dimension. But